Critical thinking using frequency distributions to understand data. A frequency distribution can help us understand the distribution of the data set, which is the nature or shape of the spread of the data over the range of values, such as bell-shaped. In statistics, we're often interested in determining whether the data have a normal distribution. We will be discussing those later on in the course. Now, data that have an approximately normal distribution are characterized by a frequency distribution with the following features. Now, the frequencies start low, then increase to one or two high frequencies, and then decrease to a low frequency. The distribution is approximately symmetric. The frequencies preceding the maximum frequency should be roughly a mirror image of those that follow the maximum frequency. Now, if we take a look at the table below, the table satisfies the two conditions. Now, the frequencies start low at 2, right? So it starts low, and then it increases to the maximum of 18, and then it decreases to a low frequency. Also, the frequencies 10, 4, and 2 follow the maximum. Therefore, real data sets are usually not so perfect as the table below, and judgment must be used to determine whether the distribution comes closely enough to satisfy those conditions. So what I'm going to do is I'm going to show you what this looks like if I kind of rotate this a little bit. So I'm going to rotate this data, okay? And I want to show you something here. So you see the value of 2, right? So technically, if it's 2, that means that the data, if it's a bell curve, starts low. Then it goes to 4, and then it goes to 10, and then it goes up to 18, which is the maximum peak. And then it's going to go back down to 10, and then down to 4, and then down to 2. Okay, that's a normal distribution because it's showing some sort of bell curve that when you cut it in half, it shows that it's symmetric. One side looks approximately equal to the other side. Now, if we consider the Los Angeles commute times from the table below and their frequency distribution, we see that the frequencies start low at 6, and then it increases quickly to 18, which is the maximum, and then decreases to a frequency of 1. Now, the distribution is far from symmetric, so the data do not satisfy the criteria for being a normal distribution. The Los Angeles commute times have some other distribution that is clearly not a normal distribution. So again, as you can see here, it starts at 6, and then it goes all the way up to 18 here. This is the maximum. And then it starts decreasing at 14, and then it starts getting really low here because it's 1. And you can see here I rotated that so you can see what that looks like. Therefore, this doesn't resemble what we did in the previous step. Now, analysis of last digits. Frequency of last digits sometimes reveal how the data were collected or measured. Example 4, exploring data. How were the pulse rates measured? Upon examination of measured pulse rates from 2,210 adults included in the National Health and Examination Survey, the last digits of the recorded pulse rates are identified, and the frequency distribution for those last digits is as shown in the table below, over here to the right. Here are the last digits of pulse rates from the National Health and Examination Survey. So here you can see the last digit of the pulse rate of 0, the frequency is 455. For 1, it is 0. For 2, the pulse rate is 461. For 3 pulse rate, you have the frequency is 0. Now, here is an important observation of those last digits. All of the last digits are even numbers. Because if you look here, all the odd numbers have a 0 frequency. Okay? If the pulse rates are counted for 1 full minute, there would surely be a large number of them ending with an odd digit. So what happened? One reasonable explanation is that even though the pulse rates are the number of heartbeats in 1 minute, they were likely counted for 30 seconds and the number of beats doubled. The original pulse rates are not all multiples of 4, so we can rule out a procedure for counting for 15 seconds and then multiplying by 4. Analysis of these last digits reveals to us the method used to obtain these data. In many surveys, we can determine that surveyed subjects were asked to report some values, such as their weight, heights, or weights. Because disproportionately many values end in 0 or 5, this is a strong clue that the respondent is rounding instead of being physically measured. Gaps. The presence of gaps can show that the data are from 2 or more different populations. However, the converse is not true, because data from different populations do not necessarily result in gaps. In example 5, we're exploring data and what does a gap tell us. So let's take a look at this table to the right over here. This is randomly selected pennies. Here are the classes, the weight in grams of penny. So we have our frequency for the first class, which is 18. The second class is 19. And then for the next 3 classes, we get a 0 frequency. And then we have frequencies for the last 3 classes. Now the table to the right again is a frequency distribution of the weights in grams of randomly selected pennies. Examination of the frequency reveals a large gap here between the lightest pennies and the heaviest pennies. This suggests that we have 2 different populations. That means pennies made before 1983 are 95% copper and 5% zinc. But pennies made after 1983 are 2.5% copper and 97.5% zinc, which would explain the large gap between the lightest pennies and the heaviest pennies.